Okay, guys, let's get started. So, this is the second video lecture from the United States. So, okay, so we learned about the virtual memory in the previous class, right? So we learned that. So actually, when a software is executed, this address. So the memory instructions include the address, to access the main memory, right? But this address, the addresses used by the memory instructions are addresses of virtual memory. It's what we learned. But to access the real data in the real physical memory, then we need to translate this virtual memory address into physical address, right? So in order to translate the virtual address into a physical address, we require page table. And then I explained that the page tables are generated by operating systems when binary code, the thread is launched by operating systems, right? So, and then this page table is just a software data structure. Uh, it, it is just an array, okay? So, and then array data, so this array element includes the physical address from the virtual address, and then also this element includes some attributes, right, or some flavors for controlling. So, you know, memory instruction is executed, then I explained about how the virtual address is translated into physical address, right? So actually, the the first the baseline the baseline address of the page table is just stored in the page table register, right? And then using this page table register plus offset, so think about the memory instructions. When the memory instructions access array data. So we just calculate the address of the target element by computing the base address plus offset, right? The page table is the same, right? Because I explained that the page tables are just arrays, okay? And then arrays indexed by the virtual address, right? So using the virtual address, you can use the virtual address as the offset from that is the page table base address, and then so we can access the page table, and then the page table includes the attribute or flag bits such as valid bits, and then also the each entry of the page table includes the physical page number, right? So virtual page number is mapped to the physical page number, right? So and then I also mentioned that the size of a single page is usually 4 kilobyte. So which means we can just translate the upper part of the address field. So this upper part is the virtual page number, VPN. Okay, so VPN is translated into physical page number by accessing page table. Then page offset is just copied, right? So this explains how the virtual address is translated into a physical address, right? Then what's the problem? So the problem is, so actually, in chapter 2, we just assume that when the load instruction is executed, then load instruction can just, like load instruction, also the store instructions. So memory instructions are executed, then we just assume that memory instructions can directly access the physical memory. So it means the main memory, right? It's what we learned. But in reality, so to translate the virtual address into physical address, so what is required? The page table. The page table needs to be accessed, right? So it's just the same memory access, right? So, using this base address and then plus offset. Okay, offset is the virtual page number. Okay? And then using this index, we can access the page table. So, the page table is just an array, right? So then we can get the physical page number, and by using this address, like physical address, then we can access the main memory. So the problem is that, so not access a memory, actually we need to access the main memory twice, right? The first access is required for getting the physical page number from page table. And if once we get the page physical address, then using this physical address, then we can access the main memory, right? This is the, the original access, right? So whenever the memory instructions are executed, so actually the problem is that the main memory is accessed for the page table access, right? That's the problem. So we learned that the main memory is very, very slow, right? And so actually, so when the data is accessed from the main memory, then it will take long cycles, right? So that's the problem. So this is a very critical performance problem, critical performance overhead, right? So it is because not to access one data, right? Actually, we need to access the main memory twice, right? So, so, so because the main memory is very, very slow, then so we need to tackle this problem. So this is the very significant performance overhead by the virtual memory, right? And also, so actually, uh, so so we will not learn about the hierarchical the page table in this course, but actually, so if we just use the one level page table, then the page table size is very large. So think about this. The problem is that, so I mentioned that the virtual page the page table is just an array, and then this array is indexed by virtual page number, right? And then how many virtual page numbers? So for this example, the virtual page number, the the bit numbers, the bit number of bits for the virtual page number is uh, it's 36, right? So it means this page table includes the 2 to the power of 36 entries, right? So it's very huge actually. So not to avoid this storage overhead by the page table, so actually we the the CPUs just so actually the operating systems. The operating systems just use hierarchical the page table. But we'll not learn about the hierarchical page table, right? And then Actually, so I will just explain about the benefit of the page hierarchical page table. So advantage of the hierarchical page table is that we can reduce the storage overhead by the page table, right? But it's not free. The disadvantage of the hierarchical page table is that actually not to get a single physical page number, we need to access main memory many times. Okay. So actually, what is the problem? The problem is that not to get the physical page number, so we need to access the main memory, right? And then problem is the main memory is slow. So how can you solve this issue? So main memory is slow, so the CPU exploits what? CPU exploits cache. So we can also apply the caching mechanism to this page table. Right. So because the page size is very large, it's a 4 kilobyte, right? So which means this page table, one single page includes this 4 kilobyte of data. So it's actually, this is large, right? So which means, and then also because of spatial locality, so within one page, if this data is accessed, and then because of spatial locality, actually the neighbor data will be requested. So and then the neighbor data can be included in a single page because the page size is large. So what is the problem? The problem of virtual memory is that in order to access the page table, then we need to access main memory, right? And then main memory is slow. So we can apply caching mechanism like the cache hierarchy, right? And it is a good approach because, as I mentioned, the virtual page number to physical page number. So this access exhibit very strong spatial locality, very strong locality, right? Because the data will exhibit the spatial locality. So which means that the same information will be used again and again, right? So actually it's a temporal locality, right? So we can apply the cache mechanism, right? So this cache includes the what data? This cache is, so in order to access the page table, we use the virtual page number, right? And then if we access the page table using the virtual page number, then we can get the, the entry data. And then this entry data includes the physical page number and flag bits, right? Flag bits. So these bits are also called the attribute bit, right? So we can just cache this information, special cache, right? And then this special cache, it's a cache for the page table. This special cache is called the TLB. TLB means the translation look-aside buffer. Translation look-aside buffer. So this is the TLB. Okay. So TLB is just the cache for the page table, right? So because we access the page table using virtual page number, then we can also organize the TLB. The TLB is also accessed by virtual page number. So the virtual page number is split into the index part and then the tag part. So like the cache, right? So in order to access the cache, then we access the cache using memory address, right? But the part of this memory address is used as the index field of the set, cache set. Also, we store the tag, right? But the PM is the same. So we access the page table using virtual page number, right? So which means we access TLB using virtual page number. Then TLB includes the tag, like the cache, the tag. And then using this index field, we can just access the target set of the TLB. Then the TLB is the data part. Then what is this data? This data is the entry of the page table. And then this entry includes the black bits and PPN, the physical page number. So do you understand? So we can just utilize the TLB to reduce the performance overhead by page table, right? So it is called a translation leukocyte buffer TLB. Okay. So because the data exhibit the very strong locality, the spatial locality, actually the misrate. The misrate of this TLB is very low. So it's lower than the cache, right? Obviously, right? So using the TLB, so we can reduce the performance overhead by accessing the page table. Okay? So let's see how the TLB works using the page table. So as I mentioned, we can just access the TLB entries using virtual page number, the VPN, right? And the part of the virtual page number is used as the index of the set of TLB, and then we use the remaining field as the tag. So using this index, we can access the TLB set, right? And then this TLB just shows the direct mapped cache, right? Direct mapped TLB, right? So it means one set of TLB just includes the one page table entry, right? So index field, we can access the TLB, and then we need to match the tag, right? We need to compare the tag. You can find the tag here, and then the tag is matched. It is the TLB heap. So what does that mean? The page table entry data. Page table entry data is found in the TLB. Then we can quickly get the physical page number from the target TLB entry. Then we can just translate we can get the physical address, like the PPN, and concatenate with the page offset, right? Then using this PPN, the physical address, then we can access the memory hierarchy, right? So, but TLB is also cache, so which means that uh, the TLB miss can be encountered, obviously, right? Because the TLB is the cache. In this case, so if the TLB is missed for this virtual page number, then we can access the page table, right? And then if the page table includes the valid page table entry, so which means the the target page is in the physical memory, right? So we can get uh, the PPN, the like, physical page number, and using this PPN and plus the page offset, and we can access the physical memory, right? And then the TLB is missed for this PPN, and this information is allocated in the TLB. Because in this case, because the page table is needs to be accessed, then it will take many cycles for accessing the page table. So best case is TLB here, obviously. And then if the TLB is missed, then the page table, we need to access the page table. So and then if the valid page table entry is found, then we can access the physical memory. But what is the worst case? The worst case is that we cannot find the valid page table entry for this virtual page number. So this is the page fault. And this is the exception, right? So exception is to be handled by detected by. So you know the page fault can be detected by hardware, right? But this page fault is handled by exception handler, right? So this is the page fault handler, right? And the page in the storage is to be allocated to the physical memory, and then the page table needs to be updated. Okay? So TLB. Okay, so you can you need to understand how the TLB is used. So I explained that the TLB is the cache for page table. So you can access the TLB using the VPN, the virtual page number, right? Then we can get the page table entry. So also, I also explained about the page table TLB misses, right? So then, so I explained about the first the TLB hit. So this is the best case. Then TLB miss. So TLB is missed. Then we need to access the page table. So then we have also the two cases. Valid PTE is found, then you can get the PPN. But if the valid PTE is not found, it's a page fault, right? Okay, so this slide just explains these scenarios. Okay, so usually the TLB miss can be handled by hardware. So sometimes the TLB miss can be also handled by operating systems. So which means the TLB misses can be handled like the, the exceptions, right? But usually we can just handle the TLB misses using hardware. Okay? And then as I explained, the page fault, if the page fault is detected, then it is a kind of exceptions, right? And then the page fault is handled like the common exceptions. So it means the recoverable exceptions. So we will learn how to handle the exceptions, right? In chapter 4, right? So then, so actually, so then how the TLB works with the cache, right? So actually the cache. So we learned about the memory hierarchy, right? So this is the cache and then the memory. Okay. So this is the actually so physical memory. So what does it mean? Actually, when the cache is accessed, then we need to use the physical address. Okay, physical address, right? Now, how can we get the physical address? So firstly, we need to access the TLB, and then good news is that the TLB hit rate is very, very high, right? Then we can get a valid page table entry from the TLB, right? So if we can get the valid physical page number from the TLB, then we can get the physical address. And then using this physical address, then we can access the cache. Okay? Then we can, if the cache, if the request is a cache hit, then we can get the request data in the cache, right? So, because the cache, so in the memory hierarchy, so this cache is actually this memory is the physical memory, right? So we need to access the cache using physical address. Okay, and then in order to get the physical address, then we need to firstly access the TLB. So what's the problem? So when we learned about the performance of a cache, for example, the average memory access, the AMAT, we learned about the AMAT. So how can we calculate the AMAT? It's the hit time plus the miss rate multiplied by miss penalty, right? So this hit time is also critical for the performance of cache. But what is the problem? Actually, in order to get the physical address used by cache access, firstly, we need to access the TLB. So TLB is also the memory component. So it means it's also kind of cache. So it means a CPU will take cycles for accessing TLB. And then using the physical address from the TLB, we can access the cache. So TLB access latency or TLB access cycles needs to be included in this hit time, which means the hit time is increased. So this is not good, right? This is not good for the performance. So for example, so if the hit time is 2 cycles, right, because of the TLB excesses, then which means so also uh so the inner text is the instruction. So actually the instruction also we also need to access instructions using the physical address. So which means that the TLB is also required for instruction cache. So actually, for the level 1 TLB, there are two types of TLB, such as the two types of level 1 caches, like ITLB is the instruction TLB, and then DTLB is the data TLB. Okay, so ITLB is used for the L1 iCache, the the level 1 instruction cache. And then DTLB is used for the, obviously, L1 cache, right? So because of TLB, then the performance, heat time is increased. And if the heat time is larger than the 1 cycle, what's the problem? The problem is that uh, the pipeline can be stalled, right? So this is the problem. So sometimes in order to reduce uh, this heat time, right? Then we can access the level 1 cache using virtual address. But it also causes some several issues, but we will not about these issues. But you can just understand that so because of these performance issues, so we can access the level 1 cache using virtual addresses. How about the instructions? So actually ITLB access can be included in the pipeline steps of the instruction fetch, right? So actually in this course, we just assume that the instruction fetch consumes only 1 cycle, but actually it's not. In the real CPUs, actually the instruction fetch takes longer cycles. So instruction fetch is partitioned into multiple pipeline steps. Okay, so that's how TLP is worked. And then the memory protection. So actually the original purpose of virtual memory is to use the main memory as the cache, right? But I explained that actually we can use the virtual memory for managing the memory space for multiple processes or multiple threads, right? Also, we can use the virtual memory for the data protection. So this is because the page table entry includes the, the flag bits. I also mentioned that these bits are called the attribution bits. So operating system can set the various attribution bits for controlling some different purposes. So we can use the valid bit, right? Also, we can use the dirty bit. It's because I explained that we use write back policy for the page table, right? Also, there are several fields such as the permissions, such as the read, write, right? Also, operating system also set the protection bits for the page table entry. So it adjusts the privilege level or permissions for accessing the target pages. Okay. So for example, very uh, critical pages such as the corner pages need to be protected, right? Then this means so some user programs can we need to prevent the accessing of the corner space by user programs, right? So the memory, you can also use this protection bits for this purpose. Okay, so 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 data protection or security. So security is also very critical problems in the computer systems, right? Uh, but it's very, very important, right? So using the page table, the hardware and also operating system can support some security controls. Okay. Okay. This is so we can use the virtual memory concept for some different purposes. Okay. Uh, so I will not explain about the cache coherence because the cache coherence is related to the some multi-core architectures. But in this course, so we do not learn about the multi-core architecture. So actually, uh, we briefly learn about some parallel processors in chapter 6 in the next chapter. But actually, we will not learn about some issues. So these issues can be critical, but we will not learn about these issues. So cache coherence is issues uh, caused by multi-core architecture. Because we skip this part. Okay, so so when you take the advanced computer architecture course, then you can learn about this cache coherence topics. Okay? So so we learned about the virtual memory. Okay, so you need to understand about the concept of virtual memory, and then we also learned about the page table and TLB. So we also need to understand how the page table and TLB work within a CPU. So, homework. So I posted the homework assignment. So also you can find the homework questions regarding this TLB and page table. Okay. I hope every student can understand this virtual memory concept and then how to support and then the operating system support for virtual memory. Okay. Okay, so if you read the CPU document, you can find the cache organizations. Okay, so this table shows the cache organizations of ARM CPU and Intel CPU. As you can see, the Intel CPU includes up to level 3 caches, right? And then usually these the level 2 up to the level 2 caches. So for the Intel CPU, right? So level 2 cache is the private cache. Also level 1 cache is the private cache, but level 3 cache is shared by multiple cores, usually in Intel or AMD CPUs. Also, you can find the TLB organizations here. Okay. You can find the virtual address field, the bit number of bits for the virtual address, also the number of bits for the physical address. So this is the maximum bit. Then its maximum bits determines the maximum memory size supported by CPU. Also, this virtual memory bit, virtual address bit determines the size of a virtual memory space, right? You can also find the TLB configurations. Okay, so in chapter 5, so when we mention the chapter 4 or chapter 5 and chapter 6, these chapters are the chapters of a textbook, not my lecture slide. So, actually the slide number for the memory hierarchy is number 7, right? But I frequently mention this is the chapter 5, right? Because the chapter 5 of the textbook actually covers the memory hierarchy. Okay. So we learned about the memory hierarchy, then cache, and then virtual memory. So, these are very important topics because, as I mentioned, memory system, the performance of memory systems is very critical, critical for the performance of overall computer systems. Okay, so I will stop here. Okay, so because I covers until the end of the chapter 6, and then for the last lecture, I will briefly cover the chapter 6 of the textbook. So, so I think it's okay. So because I covered the virtual memory part. The today's lecture. Okay, I complete the virtual memory topics in the today's lecture. Okay, so I stop here, and then I hope the virtual memory is also very important topic, right? So I hope the student can understand this concept of virtual memory. Okay, and then when you after I return to Korea, and I will also record the last lecture, and then I will post the last lecture. So on the uh, Saturday, right? Okay, so thank you for attention, and then see you in the next lecture. Okay, 감사합니다.